Alright, so today we'll go over optimization, and the optimum state of something is the best state, so we're trying to make the best of situations, and that could be maximizing something or minimizing something. So if we want to here largest rectangular area, we want to maximize the area. But if we were talking about cost in a business, we'd want to minimize the cost or maximize the profit. So it could be a maximum or a minimum. And let's look at some steps we can use to apply to any different optimization problem. And that is, let's start by doing guess and check. And that's where we just guess the answer and see if we're right. And by doing that, we will start to characterize how the numbers are related. So we have 4 inches of string, and that means we could have a 1.5 length here and a 0.5 there, because this adds up to 4. And then we can find that area. 0.5 times 1.5 is 0.75. So is that the largest area? Well, let's check another one. How about 1 by 1? The perimeter is 4, the length of the string is 4, and the area is 1. So that means this one's better than that one if we have a larger area. And what if we go to 1.75 and 0.25? So the perimeter is still 4, and the area, when we multiply that, is 0.375. So right now, that is the maximum area. Now let's generalize. Generalize just means use variables to represent all the changing numbers. So then we'll talk about x and y, and we can say that the area is x times y, and we want to maximize that. But we also, if we look at this a, x, and y, we have 3 variables. Whenever you have 3 or more variables, you need to eliminate a variable. And here we know that the perimeter is 2x plus 2y. So by having this extra equation, we can substitute and eliminate one of the variables. So we have this system of equations, and let's isolate y. So we have a equals xy, and then we have 4 minus 2x over 2 equals y. We have a system of equations. Here we have a system of equations, and let's substitute. So now we have a equals x times, and we'll go 4 divided by 2 is 2, 2 divided by 2 is 1, and that's the equation for area with 2 variables. We're going to do the derivative, so why don't we just make it a polynomial instead of a product rule. Then step 3 is absolute maximum. And we just follow the steps that we learned for absolute maximum. We need critical numbers. Critical numbers are when a prime is 0 or a prime is undefined. And a prime is 2 minus 2x. Take the derivative of the area, and then we have a prime equals 0, and we'll get never undefined. And the procedure for absolute maximum is then to check the endpoints and the critical number. And usually I'm going to say it's always the critical number, but let's see what the smallest x value is. If we were making this rectangle, x could be 0 and y could be 2, and then we'd have an area of 0. or we could have y 0 and x equals 2, so that's the maximum that x can be. And then we just use the formula for area: 2 times 0 minus 0 squared, 2 times 1 minus 1 squared, 2 times 2 minus 2 squared. So we know that the maximum area is 1, and it occurs when x equals 1 and y equals 1. And why don't we just come to this next. So skip some space, and we're going to do this one next. Alright, so pause the video and try this one. Remember to guess and check. You're going to draw some pictures, then generalize with some variables and find the absolute maximum. So step 1 is to guess and check. And we have the rectangular sheet, 10 by 5, and we're going to cut squares out of the corners. How big of a square should we cut? And also, when we fold it up, the length of the square is the height of the box. So if we cut that square up and fold up the side, we get this, where whatever length is cut, here let's cut out a 1, well that'll be the height. So in this case, if we cut 1-inch squares out, we'd have 3 left up here because the length is 5, so that'll be 5, and then we have 10 minus 2, and that'll be an 8. So we have 3 and 8, and we can find the volume to be 24. Let's try again. And we can cut 2-inch squares out. So if that's 5 and we cut out 4, there's 1 left. And here we have a 10, cut out 4, and there's 6 left. So that means we have 6 and 1. The height is 2, and the volume is 1 times 6 times 2, 12. We're trying to maximize the volume, so that's the winner right now. Try another one. And I can't go to 3. You can't cut 3 out because that'd be cutting 6 out of 5. So here we've established a maximum value for what we cut out. It would be 2.5. So let's try a half. And if I cut a total of 1 inch out of 5, there's 4 left. Cut a total of 1 inch out of 10, and there's 9 left. So now the box is 4 by 9 by a half. And that gives us 36 times a half is 18. So that's still the winner. And let's generalize. So just looking at the repetitive steps we did, how we're changing the numbers, those changing numbers are variables. So we kept changing the side lengths of the square, and then we can figure out that this is going to be 5 minus 2x, and this is 10 minus 2x, just like we did with numbers, giving a box with dimensions 5 minus 2x, 10 minus 2x, and x. The volume is x times 10 minus 2x times 5 minus 2x. And we only have two variables, so we don't need to look for another equation to eliminate a variable, but we can still follow the same steps. And if we distribute all of that, we have 4x cubed minus 30x squared plus 50x. Then we find the absolute maximum of the volume. So there's volume, we'll need the derivative, find the critical number, and check it. We need critical numbers, and we need the derivative, and that's 12x squared minus 60x plus 50. So we want to know when that equals 0. We can reduce it by 2, but we're going to end up using the quadratic formula. So we'll just do the quadratic formula. Let's go ahead and reduce it. So divide everything by 2 and we get 6x squared minus 30x plus 25. And then we'll do the quadratic formula. X equals negative b plus or minus square root b squared minus 4ac over 2a. So x equals 3.943 and x equals 1.0566. So we know that the biggest x can be is 2.5. This is too big, so that looks like it's going to give the maximum volume, and we'll check. The smallest that x could be is 0. The largest that x could be is 2.5, and we are going to check the critical number. When you put a 0 into the volume, you get 0, and without calculating, we know that when we have this would remove the height, it wouldn't have any height at all. So then the volume would be 0 there. When you substitute this into that, we have 24.056. So we got a little larger volume than what we found by guess and check. Come back to this one, and we want to minimize the sum of two numbers whose product is 192. So now we don't have a geometric shape, and we just guess. We know that the product is 192. So let's just choose numbers that have a product of 192. We know that that is 192, and the sum is 193. So if that's the smallest sum, then 1 and 192 are the two numbers. Let's try 96 times 2. That's 192, but 96 plus 2 is 98. Well, that is a smaller sum, and we're trying to minimize the sum, so now we're at 96 and 2 instead of 1 and 192. 64 times 3 is 192. 64 plus 3 is 67, and that's an even smaller sum. So we could keep on going, but we see the relations, and we can generalize. We know that we're going to have two numbers, x times y equals 192, and we need x plus y to be the sum, and we want to minimize the sum. So this is the equation we're going to work with, and that's the equation we'll use to eliminate a variable. We have three variables. We don't want to take the derivative with three variables, so we're going to substitute. Here's the system, and we're going to let's solve for x. So we'll have x equals 192 over y. Solving this equation for x, x plus y equals s. And then we have s equals, x is 192 over y. That's a y plus y. So we have this equation that we're going to optimize, and we substituted for x. And this is going to be a little easier if we get a common denominator. So let's multiply this by y over y. We have 192 plus y squared over y. We have y squared over y. We have a common denominator, so there's the combined function. Now we need the derivative of that, so we can just say s prime is, we'll use the quotient rule, and we have the denominator times the derivative of the numerator, 192 plus y squared, the numerator, times the derivative of the denominator over the denominator squared. That's going to be 2y squared minus 192 minus y squared. Y squared minus 192 over y squared. All right, so we have the derivative, and now let's do the absolute maximum, and we need the critical numbers. That's when s prime is 0 or s prime is undefined. Okay, a fraction is 0 when the numerator is 0. And we would have positive or negative here, but it says there are two positive numbers, so we ignore the negative. And s prime is undefined. The derivative is undefined when y equals 0. And let's check the endpoints and the sum. We want to find the minimum sum. We can't use 0 because if you use a 0, you would have you wouldn't have a product of 192, so that's why it's undefined. But if we just use a very small number, we can see that when we plug that into this, y squared minus 192 over y squared, this is going to be a very large number. So we want a minimum sum, and this is giving us a, sorry, let's correct that. We need to put this into 192 plus y squared over y. So we are checking the values of the sum. We're not checking the values of the derivative. The sum would be 192,000. We want a minimum, so let's check 190, square root of 192. We substitute it in there, and we have 27.713. And we could have a 192 would be the largest value, and that is this one. If one of the values is 192, the other one has to be 1. And we know that that sum is 193. So here we found the minimum sum is this number occurring when y equals radical 192. And then we can use this to find the value of x. X would be 192 over radical 192. So let's just finish that. We say y equals radical 192 and x equals 192 over radical 192. All right. So this is, you were adding two numbers, and the first number is squared, and then we're adding it to the second number, and that sum is 27. If you take the two numbers, not squaring them, you want to find out the maximum product. So pause the video and try this one. Okay, let's just try 5 squared plus, that'll be 25 plus 2. We know that this has to happen, so that's the constraint. We want to maximize the product. So now we find the product of 5 and 2, and we get 10. And now we can just start adjusting. What if we did 2 squared plus 23? We know that's 27. And 2 times 23 is 46. We're trying to maximize the product, so right now that's in the lead. 1 squared plus 26 is 27, and we have 1 times 26 is 26. So we're looking for something around there maybe. Let's generalize. And we just see this pattern repeated, and the numbers that are changing. X squared plus y has to be 27, and then x times y is the product, and we're going to maximize the product. We're going to use this equation to substitute into this equation so that we get rid of one variable. Let's just solve for y, and we're going to have y equals 27 minus x squared, xy equals p, and that would give us, substituting for y, we have 27 minus x squared equals p, and we can have 27x minus x cubed equals p. Let's find the absolute maximum. To do that, we need the derivative, and that's going to be negative 3x squared plus 27. And we'll find the critical numbers. P prime equals 0. P prime is never undefined because it's a polynomial. So we have negative 3x squared plus 27 equals 0. Okay. We have positive or negative. Do we need the negative? Let's check. The sum of the first number squared and the second number is 27. Maximize the product. Well, let's check. Maximize the product. We wouldn't consider the negative here because the product's going to be negative. So let's look at values of x and the product. We can just think of what's happening when x is very small, and we put that into the product. We have 0.27. Well, here's the critical number, and that gives us 54. Here we would have some number that's close to or a little over 5, and we end up getting a very small number. Like, what if I just chose 5.18 and we have 0.868? I know that this can't go to 6 because if we square 6, then it would be too big. Okay, so now we have the maximum. And why don't we just save this so we don't have to worry about the negative, because maybe I'm wrong about not including it. Let's just say the sum of, let's say the numbers are positive, and then we won't have to worry about the negative. All right, and we'll stop there.